Do wormholes exist? We don't know. See, the wormholes, for them to exist, they would have to be sustained. If they exist at all, they're short-lived. Because gravity wants to keep them closing in. Right? In other words, they have to be sustained outwards by negative or exotic matter. And so the only way we know that can happen is if somebody, an alien or humans, whatever, are injecting energy into the wormhole to keep it sustained and open. They don't, in other words, it's highly unlikely that they naturally exist. And furthermore, they're still hypothetical. We don't know if that's possible yet. I believe AI has a level of consciousness. No, I don't think AI is conscious. I think that you don't just get consciousness from information processing. It's part of it, but it's not the totality of consciousness. There's a lot more involved with consciousness. I don't think we could understand it enough yet to say AI is or is not. Is space another planet we are in? No, space is the boundary of our universe. The Earth is just, we're bounded by the Earth. It's just our world. But there's other worlds out there. Countless other worlds, planets, stars. There's more stars in the universe that we know of than grains of sand on all the beaches of the Earth combined. It's a lot of stars. What did the James Webb really see that they are not telling us? So there's nothing to hide. They're not hiding aliens or, I know from your perspective, it's when the common public is exposed to these really crazy images from space that are so foreign to our daily lives. It seems that there's something else. There's got to be something more. But in reality, the scientists are just people like you and me. They're not hiding anything that, they're not hiding aliens or something. How do you feel about Europa? I think it's an interesting planet, moon. Very interesting world. I think I have Now, there's actually, when it comes to Europa, there's actually been recent challenges to this ocean beyond underneath the ice of Europa. Now we're kind of questioning it more as we study Europa more and more. There actually may not be as much water on it as we thought. But still a very prime candidate for potential life. So here's Europa, by the way. These incredible... This is a moon of Saturn. Or, Jupiter. These stripes and lines indicate that it has water or some liquid under the surface, under the ice, that's trying to penetrate. As Europa moves around Jupiter, it gets tugged by Jupiter, right? So there's tension. This generates heat. So these moons around Jupiter are actually heated internally. There's friction, heat it's generated inside this moon, and that's why even in this very cold area of the solar system, there's still liquid water under the ice here that can seep sometimes up through the surface and create this plume of water vapor and snow and ice out into the surface of Europa. However, scientists are not quite sure yet if they actually exist. We do know they exist on Enceladus. This is a moon of Saturn. Saturn has lots of water. We know, we've seen it, we've observed it, and we have observed with cameras. They're plumes that contain amino acids. So Enceladus is quite a remarkable object. All right, let me get back to some questions. Is it possible a civilization as old as Milky Way exists? Sure, the universe as we know it is about 14 billion years old. It took about 400 million years for the first stars and early galaxies to form. And so if perhaps life emerged on those very first stars, around those very first stars and galaxies, it's plausible that they could still be living today, 13 billion years later. And so our galaxy is about 11, 12 billion years old. And so, yeah, it's pretty plausible that there are aliens out there somewhere in the universe that are 13 billion years old. That's how old their civilization is. Very possible, but extremely hypothetical. Is it true that the sun will destroy our planet, nothing will exist? Okay, so our sun, when it dies, as it burns its fuel, the sun burns hydrogen right now, right as we speak. Inside the core of the sun, it's fusing hydrogen atoms and nuclei together, turning into helium. Helium fuses into carbon, nuclei, and that gives us light and energy, right? That process. But the sun is not massive enough to burn carbon. It can't fuse carbon together. It's too small. The pressures inside are just too weak. So once it burns up all its helium, that's it. The sun is done. It dies. And so once that happens, the sun will shrink a little bit. Well, first it will turn into a red giant. First it will succumb to the interior forces. But once it gives its last gasp of breath, it shrinks into a white dwarf. A white dwarf is a star that doesn't really produce light. It's just cold and dark. It just gives off heat from leftover radiation inside. But it's as small as the Earth. It's a star as small as the Earth, but with the mass of about 100,000 times the Earth. And so it will remain that way. And in fact, it will turn out to be something like this. If you notice here in the middle, there's a little dot. That's a white dwarf. So our sun will end up like this. And all that gas around it, that's just the gas from the star. Helium, carbon, all the elements that were superheated will slowly evaporate away from the star. It'll shed off at that radiation. It'll turn into this planetary nebula. That is the future of our sun, and it's going to take 5 billion years to get there, but it's going to be quite a thing to see. Now, the Earth will be engulfed by the sun as it turns into a red giant. The sun will get so big that it will come all the way, eat away at Mercury, into Mercury's orbit, eat away into Venus's orbit, and even into Earth's orbit. So we will likely be turned into vapor, will vaporize by the sun in about 2 billion years. 2 or 3 billion years, it'll get that big. And so, yeah, if we don't move, if we don't go to another planet or another system out there, we are toast. If we stay on the Earth, we're toast. We have to move out into other solar systems and star systems and planets. But we have some time to do that. We have a few 100 million years. Okay. How sure are we that Einstein's theory of space-time is true, including the bending of space? Well, in science, we measure theories or ideas by their utility. How useful are they? And Einstein's relativity is extremely useful. And by the way, so is Newtonian mechanics, extremely useful. However, they both have different scopes of ways to be useful for how we understand the world. For example, Newtonian physics allows us to, with very good confidence, determine the planetary motions, the motions of the worlds of the sun. But when it comes to smaller masses, the sizes of people or smaller objects, in the more complicated planetary motions, it doesn't really account for those very well. You need Einstein's gravitational laws and theories to account for those more complicated and smaller things, right? So that's why his work's there. However, there's a limit to even Einstein's theory. And that's where quantum mechanics comes in, right? When it comes to black holes or, the Big Bang, Einstein's laws in physics stops working. It just stops working. We don't know what's inside a black hole by using Einstein's equations. We need quantum mechanics. And we still don't yet have a quantum gravity theory. We don't have a theory of quantum gravity yet. We're still working on it. But yeah, Einstein's theory of relativity works. It helps us send out satellites into orbit. We couldn't use satellites if it weren't for Einstein, because he understood time dilation. When you put out satellites into orbit, the gravity is different, its speeds are different, and so you have to account for that. That's time dilation. In other words, satellites' times are different from our time. And so that's where Einstein shines. However, when it comes to black holes or things like that, it doesn't work. How do we know what actually happens inside a black hole, or is it just theory? Well, it's at the moment hypothetical mostly. We have understanding of how black holes operate. There are certain types of black holes, some are larger than others. There's supermassive ones, right? There's rotating black holes that rotate. Space-time itself, it's like a funnel. So we can calculate those kinds of things. We can understand space and time to a degree, what happens at the event horizon. But going past the event horizon gets tricky, because that's when gravity gets so small. That's when energy gets so small. You need quantum mechanics. And there's some ideas in quantum mechanics that say, well, if you go into a black hole, quantum mechanical laws take effect, and you end up somewhere else in the universe. If you go through the black hole, you end up through a white hole, or end up in some other place in the universe, like a quantum jump or a quantum leap. We don't really know. We're not very confident, but we're working on it. Okay. Will humans in 2 billion years be able to colonize a different, younger solar system? We can do it. Yeah, we can do that technically today if we wanted to, but it would be very difficult. It would also take a long time to get to the nearest star. With current technology, it would take like thousands of years to get to the next star. And, within 2 billion years, that's a long time to develop technology. Perhaps we'll have antimatter rockets, or, relativistic space travel, where we have rockets that can somehow distort space-time and allow us to ride gravity waves to another star system. Very possible that we do that in the future. How much does a pulsar spin when you blink one time? Pulsars spin very quickly. We're talking thousands of revolutions in a minute. Tens of thousands. Do you think we'll even be around in 1 million years? We won't be around in 1 million years, but our descendants will, hopefully. And our descendants will hopefully be smarter, more intelligent, more capable than we. Just as we are smarter and more capable than our ancestors. So hopefully that trend continues. Evolution doesn't stop. And so I would hope that the people after us are much more capable than we. Is it true that every day the moon moves away from Earth? Yes, every day the moon, every year, I mean, on a daily basis is very small, but on a yearly basis, the moon's moving a couple inches away from us because of certain small, tiny differences in masses and things like that. Relativistic reasons why the moon is moving just slightly away from us every year. When the Earth formed 4 billion years ago, the moon was far closer. It was much closer. In fact, in the early Earth, the tides were way stronger because that's what the moon does. The moon gives rise to tides on our planet. And so in the early Earth, even ponds and even lakes, you could see the tides more clearly. Do you think there are some other ways that space and time could be warped that we don't know of? Absolutely. Space-time may be emergent, right? They're like in string theory. Space-time is made of, strings, right? You have all kinds of quantum mechanical theories where space and time is made of entanglement. It's actually made of wormholes, essentially. That the fabric of the universe is actually wormholes. Very strange ideas when you, in regards to us being here, will we evolve much more? I feel we've evolved so much. Well, evolution is slowing in us. Natural selection is no longer taking place in us as much as it did 100,000 years ago because we have technology. We have medicine, technology that keeps us alive past the point where 1,000 years ago we would have been dead due to natural selection, right? So we can kind of slow down natural selection. People with disabilities, people with illnesses that 1,000 years ago would have rendered them dead, today they're still alive. And so they can still pass down their genes, and so those genes still are in the mix. So yeah, we're not evolving through natural selection. However, we are evolving in other ways, in intelligence, technology, ability, power, energy. These are ways we're in a sense evolving, and I think there's a lot to go in that sense. There's a lot to learn. There's a lot for us to do. If it falls around the Earth, how it leaves Earth orbit? I don't know what you mean. So when a rocket launches, it doesn't launch straight up to space. It launches very slowly. Most rockets maybe go 30, 40 miles an hour as right when they lift off, but they go up and they arch. They turn sideways around the Earth to pick up enough speed, and then they leave, right? So they kind of circle around the Earth into orbit and then leave with just enough escape velocity. Yeah, that's how you leave the Earth. Going straight up would not be possible. You can't just go straight up. That would be, you wouldn't be able to, gravity gets so strong that you wouldn't be able to do that. You have to have a lot more rocket fuel. You'd have to have a lot more energy to do that, straight up. Going around orbit, picking up speed around orbit is how it's done. All right. Could, in theory, gravity stop and we all just go flying off the Earth, and would the Earth drop? Well, if gravity stopped, yeah, we would fly off the Earth. Why is gravity so much weaker than the other fundamental forces? That's a great question. We don't know the answer to that question. Why? Why is gravity so much weaker? Again, there's something that quantum gravity can explain to us. Wouldn't it logically be impossible to do time travel to the past because of time paradoxes? Yeah, there's some that say that, but yeah, technically it is impossible for many different reasons, but yeah, there definitely can be time paradoxes. How could you go back in time and meet your family? If what if you disrupt your parent, like in Back to the Future, right? If you disrupt your parents from meeting, they never make you, then how could you be there in the first place to go back in time if you were never made? But that assumes that there's one timeline. What if time forks? What if there's multiple timelines? What if, as we speak, multiple timelines are branching off out of me? And when I go back in time, I'm not really going back into one particular timeline. I'm going back into somebody else's timeline. These are all questions we don't have answers to. But yeah, great question. Why would we want to colonize Mars? And would humans be able to return to Earth? So in the 1960s, we went to the moon because we wanted to beat the Russians there. We wanted to flaunt our nuclear capabilities. We wanted to be the best, right? And that's why we went. Then we stopped as soon as the Russians lost, right? We stopped going. It took a lot of money and effort to do that, right? Now we're going back to the moon because guess who? China is going to the moon in 2030. Or we want to beat them there, right? But also, not just China is going there, but also there's an emerging vision that many people have about a new space economy. Imagine being able to mine in space. Imagine having another planet to go into, to just visit, like on Mars, or just live there forever if you want to, right? Imagine tourism on Mars. Imagine being able to one day in the future take a vacation to Mars and go see what's going on there and come back. That's possible. And that is only going to happen if we go to space and we settle there and we build there and we make space a kind of economic endeavor. Just like, asking that question is like, oh, why would we want to colonize the Americas? Well, resources. They want to go there for resources, to see what's there, right? Land. Humans are exploratory. We like to explore. And I think that this is no different. I think going to Mars, going to space is no different. It's speaking to that human need to want to explore and expand. If we want to make big discoveries, we need to just say China want to do it first? Yeah, next time we want to make a discovery, just say China's doing it, and you Americans will be rushing to get it done. Is consciousness an emergent property or something fundamental? I think consciousness is clearly emergent. I think that when we talk about consciousness, we're talking about something that happens in a brain under a certain biochemical machinery. I think that's all we're talking about. I don't think there's anything special happening when you have a thought. I don't think that thoughts are things that are fundamental. I think that's just happening in your brain. Mike, how do I convince my friends that dinosaurs are real? Oh my God, Where do you live? Kentucky? So the reason why, look, when you're confronting people like that, typically they're fundamentalist Christians or whatever, try to reach them where they are. Don't say, oh, dinosaurs are real, trust me, don't just say that. You have to speak to them from their perspective. And, ask them questions about their view. Ask them, why is it that we see the KT boundary, right? The boundary where there's lots of iridium. How did that get there? How do we see all these fossils? Where do they come from if dinosaurs aren't real, right? Birds. Why do birds look so similar to dinosaur fossils? Oh, because birds are dinosaurs, or, try to, don't just try to talk to them to make them think that dinosaurs are real. Make them understand why and how we understand dinosaurs are real, right? Nobody wants to be told things are true. People want to know how. And that's where a lot of people get lost. They're never really properly taught the how. They're only taught the what. And that's why people go, oh, well, I have all these questions. Well, and then in that questioning, they go, okay, well, I'm not going to believe it's just too complicated for me. All we had to do is teach them how, and there wouldn't be so many people succumbing to these conspiracies. All right. Could you say the Earth is a result of star formation? In a sense, yeah. The Earth is a remnant of a star that, over time, parts of it succumb to gravity, and you get it. It solidifies. It becomes colder over time, and yeah, essentially, we're fragments of stars. Where does iron come from? When did we discover this? So I'm assuming you're alluding to the verse in the Quran that talks about iron coming from the heavens. Well, it doesn't come from the sky or the heavens or space. Iron, most of the iron on the earth, overwhelming amount of it, is inherent to the earth, inherent to the earth's formation. Most of it is in the core, in the inner and outer core. Very little of it is on the surface, and for the little bit that is on the surface, a lot of that came from asteroids. So very little of the iron on the Earth comes from space. It was inherent to the Earth's formation. And as the Earth formed, the heavier elements, the denser, more heavier elements, they naturally sunk. Iron, nickel, the heavy metals, they sunk to the core because that's what material does. The lighter stuff floats, the heavier stuff sinks. And because the Earth, remember, the whole Earth, when it was formed, was all molten. It was all liquidy. The Earth, at one point, the Earth was a ball of liquid, literally. But that's why all these materials differentiated, and we get a core that's solidified with a crust that is very less dense and fragmented. Now we have fragmented plates on the Earth's crust. That's very strange. How you have a liquidy mantle and a crust floating on top of it. Fragmented plates smashing into each other. Yeah. All right, next question. Why are we so advanced compared to any other species? Good question. The answer is because of various different factors. Number one, primates, the first primates existed in North America and the Arctic. We're talking 90 million years ago. Not technically primates, the mammals that led to us, they were thriving in the Arctic in North America But they couldn't really do much because the dinosaurs were dominant on the earth. When the dinosaurs died with the extinction, our ancestors were able to finally fill in the niches of the trees, the forests around the world. And that's when they started grasping branches and jumping through trees. And that changed how we saw, right? That changed our vision, our brain had developed for that. And then we started moving into Africa, where there was lots of fruits. So we had it, and fruits contain lots of energy. And so we started getting bigger. Our brains grew. We started hanging on branches instead of just swinging on them. We started hanging on them. Our hands became graspable. And then because of climatic events happening in East Africa, we were forced to leave the trees, and we had to start walking further and further into new habitats, fending off predators with our intelligence. We started walking upright, and that gave us an advantage of walking further distances. And we discovered through walking fire. Oh, look, lightning strikes this tree. It starts a fire. Oh, wait, let's take some sticks, use that fire, and bring it back to camp. So now we can survive the night. Now we can camp anywhere we want to. If there's a fire, we can camp out anywhere. And then we started sustaining fires, and then we started building our own fires with stones. We started smashing rocks together and go, oh, well, look, sparks. Okay, let's use this to build a fire. And now we can cook. Then we started cooking food. Oh, okay, now we can eat anything we want. I can eat potatoes. I can eat root vegetables. I can eat meat. I can eat anything. And I can carry this food. And as I walk, I can move it to the next camp. And we can trade. We can communicate with other tribes. We can talk. We can vocalize things. Ooh, I want. We used language. We used our intelligence to survive. We had no choice. We were forced to become intelligent if we wanted to survive. And it just happened that the sequence of events played out the way it did. You know, all the events that happened to make us happen were very incredible. And so now we have societies and planes and cars and civilization. So it seems like we're so much more different from the other animals, but we're really not. If you take a caveman from 10,000 years ago to a modern day chimpanzee, there's really no difference in terms of intelligence. It's very small, you know. It's the illusion that you get when you live in society that the things around you, the result of people working together collectively for the past 5,000 years. You forgot that. We're not actually that smart individually versus the other animals. It's collectively where we shine. And so, yeah, there's two things going on there. One, all the events that led up to our intelligence. Two, the illusion that we are so much more intelligent than the other animals. All right. Has anyone sat foot on the moon? Of course. We can see the footprints. We can see the flag. We can see the rover. Okay, so we have moon rocks from the moon. There are laser reflectors on the moon that we can shine a laser at and see in real time. There's no question we went to the moon. There's no way we could not have, given the evidence, given the hundreds of hours of recordings that are not on digital cameras. These are filmed. It's on film. How do you fake or Photoshop physical film? You just can't do that. And the effort it would take to fake the moon landing is so extremely outlandish. It just takes less effort to just go to the damn moon. All right. How did so many tribes know how to have languages, and then how do we translate? Language comes natural to us. That's just, look, we know that there are parts of the brain that perform language. People have been teaching each other how to speak for thousands of years, right? We think it's some novel thing we've done recently, but no. People have been teaching language for thousands of years. Now, of course, today it's more standardized. We have global languages, English, Mandarin. But, thousands of years ago, we're saying, people had different types of vocabulary, different types of utterances. But the point is that it's built into us. Language is integrated in the human being. And that's why we had so many languages, because that's just how we live. That's how we survive and how we thrive, using language. What would happen to the Earth if the core cools off? Will it happen? Yes, it will happen in a couple billion years. The Earth, the interior of the Earth gets its energy mostly from radioactive decay. The elements inside are very radioactive, and that decay gives off energy. And so that's where a lot of the energy in the core comes from. But that process will end in about 2 billion years. And once it does, we will lose our magnetic field. It'll be a very bad day to live on this planet, because you go outside, you'll get lots of radiation. We'll lose our atmosphere faster. Tectonic activity will cease, mostly. It'll be a very bad place to live in. Do I believe in a higher power? What do you mean by higher power? When people say, do you believe in God? There's 1,000 different types of ways people have contrived what God means. I don't know what a higher power is, but people say it's all smart, all intelligent, all powerful, all loving. But I don't know, I'm not convinced that these things are compatible with each other. I think there are some paradoxes there. I think there are some issues with certain versions of God. And lastly, there's an overwhelming lack of evidence for this being. And although it's natural for us to go, well, if who made all this, right? You look around and who made all this? It's a natural thing to say, but there doesn't have to be anybody making us. We tend to think people make us, a being made us, because we look around the world and we see people making other things. Houses, buildings, art, food. And so we go, okay, well, how did we get made? That's the inference we make, but I think that's an invalid inference. I don't think that we must have been made. I think that we've naturally come to be the way we are today. And that's it. The more I look into science, the more I learn about science, the less evident God becomes to me. Especially when you consider all the gratuitous suffering in the world, the suffering that is embedded in nature itself. Wild animal suffering, the fact that animals have to fight to survive every day, they have to eat each other gruesomely. Why would a loving being make that setup? Why not just make it so that the animals are all herbivorous? Or better yet, make it so that animals don't have to eat anything. They can just drink water to survive, and that's it. Why does it have to be the case that we have to eat food if God exists? But under evolution, under naturalism, under the idea that there is no God, it makes perfect sense why we'd have to eat every day, because that gives us energy, calories. And that's consumption of energy is how our life processes are sustained, because that's how it's always happened through our evolution. That's just the biological necessity of our being. But if God exists, I don't see any reason for us having to eat food every day. And by the way, people choke on their food every day and die. Like, why would God create such a weird design in our bodies? If he was so intelligent, it seems like a very non-intelligent design. All right, next question. We live in a world like NASA, but there is still inequality. I don't know what you mean. I think you mean like we live in a world with NASA where we have rocket technology and satellite technology, but there's still inequality. Yeah, I don't think that we can solve all inequality. I don't think that we'll ever be able to make the world perfect. But I can tell you that the world is a lot better today than it ever was in the past. You take a look at objectively. Take a look at the the statistics about poverty and childbirth and infant mortality and crime and disease. We find that we live in some of the best times ever, with the least poverty, the least crime, the least disease, and the best access to medicine and safe drinking water and safe food. And I think that we have it really good versus the past. Now, of course, we can improve, but the way we improve is we embrace science instead of shunning it away and taking it for granted. What triggered the Big Bang? The Big Bang could have been the result of a quantum fluctuation. In other words, there is a pocket of space-time, a quantum field that had energy fluctuating, and this randomly happens. And at one point, this fluctuation yielded space-time itself, and we have an inflationary period, a rapid inflation coming from a quantum fluctuation. That's likely how it happened. That's what the evidence shows. But I love when people say, oh, I like when people say, oh, well, what caused the Big Bang? See, it was God, because you don't have an answer. Well, first of all, we do have an answer. Number two, even if we had no idea, I don't know how the Big Bang happened. That doesn't give leeway to God existing. This is an argument from ignorance. Well, I don't know how it happened, therefore God. That's invalid. Just because we don't know doesn't mean God did it. But more importantly, we have a lot of reasons why God likely didn't do it. Quantum mechanics. And we never need to resort to God. We just don't. Can we build a base in the moon? Yeah, if we wanted to, we can build a base on the moon. But the moon would be a stepping stone to Mars. The moon has resources. There's water on the moon. And at the southern pole on the moon, there's lots of resources. Helium and water, ice, that we can extract. And we can build a little space colony on the moon. But other than that, it's very dangerous to live on the moon for a long period of time. There's a lot of radiation. There's low gravity. Mars is different. Mars has more potential, and it has far more water. If you were to melt the surface of Mars, you would melt enough water to cover the whole planet in like 3 meters of water. That's how much water there is on Mars. It's a lot of plenty of it. It's just ice underground at the poles, and so Mars has far more potential, but the moon is just a place like an outpost or a stepping stone for a Mars. I hope you find God before it's too late. Look, if God exists, why doesn't it show itself? Why doesn't it give us more evidence of its existence? Why is it so hidden. Why is it so hidden from us? If it really wants a relationship, right? Think about it. If this being wants a relationship with us so much, as you say, where is it for the people who are? You might be saying, well, Mike, you have a hardened heart. Okay, but how about the people who are sincerely wanting God to reveal itself and really want a relationship with God? Why doesn't God reach out to them? Why are they still atheist? It seems counterintuitive that a loving God whose entire purpose of humanity is to have a relationship with us never reveal itself. Especially in the modern age where 2,000 years ago it supposedly did all these miracles, so we know it can reveal itself. There's no reason why it must be hiding. If, based on your story, 2,000 years ago, it came to earth and rose on a cross or whatever. Clearly, it can reveal itself. It just seems to not want to anymore. So how is it my problem? I would say it's more God's problem if I'm not convinced of its existence. What is dark matter? So dark matter is a type of matter that is dark. No. It's invisible to any light because light doesn't interact with it. Light doesn't just shine through it. It doesn't interact with it at all. It also doesn't interact with our type of matter. If you were to hold dark matter in your hand, it would just go right through and sink through the earth. It wouldn't interact with us like that as regular matter does. If, like, for this water bottle, right? I can interact with this bottle. I can hold it in my hand. You can't do that with dark matter. It's weakly interacting. However, it has mass. It has gravitational effects on us. In fact, dark matter is everywhere in the universe. There's so much of it. There's a lot more of dark matter than our type of matter. In fact, dark matter keeps the galaxy together because it doesn't clump together like our type of matter clumps together. It doesn't interact with itself even as much as our matter does. So it doesn't tend to clump up like this. It tends to make these halos, these ghostly halos that just surround the galaxy. And because they have mass, they're gravitationally affecting us, affecting the rotation of the galactic arms in a way that keeps the galaxy stable. And that's what dark matter is. Now, we can't see it with light. We can't see it with telescopes with light, but we can see it. We can see its gravitational effect. In other words, we can look at dark matter clumps and see how light bends away from it. We can see how it affects space-time itself. The bending of space-time, we can see dark matter's effect on that. But yeah, that's how we, it's remarkable stuff. Where does gravity come from? That's a billion-dollar question. We don't know. Now, Newton in the 1600s came up with his Newtonian laws of gravity, where he said, well, why does an apple fall from a tree? He thought that the earth was attracting the apple, and it was kind of tugging on the apple, right? Makes sense. Yeah, if I take this, it drops, it falls right to the ground. It seems like the earth is attracting that to the ground. So he invented from this, he extrapolated from this, the different laws of motion. And so we can, with very good precision, understand the motions of the planets. However, Newton came along, Einstein came along and said, wait a minute. There are some things we can't explain with this. Namely the retrograde motion of Mercury. There's some very weird, peculiar planetary motions that Newtonian mechanics just doesn't account for. And that's when Einstein started thinking, well, wait a minute, maybe it's not that the Earth is tugging on this like some invisible rope tugging us down to the surface. It's more that the Earth is creating a gravitational field. It's warping space-time itself in such a way that this bottle is moving just on its same geodesic. The geodesics are aligned. That's what gravity is. It's very weird, but four-dimensionally, everything in the universe is moving through space-time at the speed of light. And what we mean is gravity is just the intersection of these geodesics in 4D space-time. Very complicated, but that's what we figured out. That's what he figured out. That it's not that gravity is a force. It's the warping of space-time itself, making the illusion that it's falling to the ground. So that's what gravity seems to be in Einstein. But now we have other questions. Okay, what happens in a black hole? We don't really know. Einstein can't figure that out. Einstein's equations don't work there. What happened before the Big Bang? Einstein's equations don't work there. The energies are just too big. And so that's where we have quantum gravity. But we don't have it fully figured out yet. There's all kinds of ideas. String theory, some ideas in string theory. Well, maybe there are gravity particles. Maybe there's gravitational gravitons or whatever. We don't know yet. We still don't know the true nature of gravity. We still don't know why we just still don't know why this happens. We still don't quite know why. We know how. We don't know why. Einstein believed in God, but Einstein did not believe in the traditional God. He did not believe in the theistic God that knows everything and loves you. He believed that the laws of nature were God. This is Spinoza's version of God, right? That God is basically the laws of physics. Okay, well, if that's what you think God is, great. Great, that's fantastic. But that doesn't mean that you think God is loving and caring and wants and died for you. That's not what Einstein believed. So when you say Einstein believed in God, it's not quite correct to say that. What is black energy? You mean dark energy? So dark energy, when we look out into the universe, we see galaxies moving away from us. Every galaxy, with the exception of a couple that are close by us, are moving away from us, and this recession is accelerating. They're moving away from us faster and faster. There's something about the universe that causes this expansion, and that's what we think dark energy could be. Dark energy is a type of force like gravity. You know, like when I was mentioning you drop something, right? That's an attractive force, essentially. According to Newton, right? This is an attractive force. But dark energy repels things from one another. It's repulsive. So instead of this dropping to my hand in an attractive way, if I were to throw this in the air, it would just go up. It will wait for me with an acceleration, right? That's what dark energy would be, this repulsive type of force. And so just like gravity attracts things with an acceleration, right? If you were to throw a ball in the air, it would come back to the earth at 9.8 meters per second squared, an acceleration, right? If you were to throw a ball in the air, it would come back to the earth at 9.8 meters per second squared, an acceleration. Dark energy works very similarly, but the opposite way. A reverse type of gravity. repulsive type of gravity. And so the idea is that the universe is full of this dark energy. It exists within space-time, but perhaps maybe a property of space-time itself, giving rise to the expansion. Now, there might be counteracting forces. It may be the case that matter, like our type of stuff, galaxies, it actually may slow down dark energy. We don't quite know yet how dark, the dynamics of dark energy. It may be, there are some signs that dark energy may actually be fluctuating in its intensity. In other words, there may be some periods where dark energy is dominant and some periods where it's not dominant. So in other words, the universe may expand and contract. Expand and contract. We don't know yet. We don't know the answer. But that's why we have James Webb and the Nancy Roman telescope and all these telescopes. We're trying to see what's happening out there to get better insight on dark energy. What's my favorite science fact? The best thing about science is that we can do it. The fact that we can even learn about the universe and understand it to any degree is fascinating to me. That's the most incredible thing about the universe, that we can learn about it in the first place. That's remarkable. I very well could have been a slug or an ant and have a much more limited scope of the universe, but I happen to be a human being. And I can understand to a large degree my place in the universe. And I can understand that, make these very deep cosmic connections between me and stars, that we're stardust. I can make these connections between me and you, that we're biologically connected, that I'm connected to the earth chemically, that I'm made of water, mostly water, which is what the earth is on the surface, is mostly made of water. There's a connection that I have between me and the world, and I can understand it. That is remarkable to me. Do you like the idea that the fifth dimension is space of branched timelines, or the string theory one? So, string theory has, for the mathematics to work, for the forces of nature to make sense in string theory, you need 11 dimensions. 11 dimensions. But these dimensions are not, like when you talk about the fifth, the sixth, they're not places where people can go, and like you can't like physically go there like as a person. These are hidden dimensions, microscopic hidden dimensions in space-time that are so small you can't see or do anything in, right? But yeah, there's all kinds of different, there's the ADS, CFT, there's all kinds of different theories about this, but I'm not going to talk more about the string theory, because I'm not a physicist. If you would be able to go to the center of the earth, how fast? What do you mean, how fast? Oh, how fast would time go? You wouldn't notice a difference in time. So, yes, there would be time dilation. So, relative to the center of the earth, the very center, there is a difference in the time dilation. But your experience of time is always the same. Even in a black hole, your experience of time is just as it is now. Your heart beats the same rate, everything is the same, no matter how fast you go, no matter what your gravity is. Remember, it's only relative that time dilates. It's only relatively speaking that my time is different from yours. depending on my reference frame. Very strange how this works, but it's hard to grasp. It really is. But yeah, you wouldn't really notice a difference. It would be negligible if you were to go to the center of the Earth in terms of how fast time would go. By the way, it's actually the opposite. Going towards the center of the Earth, you would have time would be slower for you, because the more gravity, the slower time moves relative to the Earth. That's why satellites are a bit faster. We have to account for that relativistically. We have to account for time dilation with satellites because their experience, because of the motion of them. But again, it's very negligible. Why are quantum physics and relativity incompatible? I don't know I cannot answer that question to the extent in which you want. I'm not a physicist, but all I can say is relativity works at the Planck scale. That's the limit of it, right? It's anything beyond that, it starts to just make no sense. Things go to infinities. It just doesn't make any sense. That's all I can say. I'm not a physicist here. What do you think happens when we die? I don't know. I think that as far as I've seen, I think that when people die, they just stop living. They don't have any consciousness anymore. Their heart stops. Like, that's it. And people, they get buried and that's it. They eventually erode away into the earth where they came from. And that's it. And over time, people will forget about you. Just like we forget about people a million years ago. We have no idea who they were. We don't care about them really anymore. And a million years from now, nobody's really going to care about you or me. And I know that evokes a sadness in us that makes us feel uncomfortable. And, ooh, I don't like that. I want us to go somewhere. I want to be known. I want to live again, right? There's a part of us that really wants that. But that's why we have to be extra careful and not to succumb to that emotion. Because it may not be true. And as much as it makes you comfortable to feel that you do go somewhere when you die, it's a band-aid. It's a temporary fix to a deeper problem. The deeper problem is, well, what motivates me to do the things I do, right? Ultimately, what drives me? What's my motivation for life? I think recognizing the finitude of it, I think recognizing that we don't have an afterlife, I think facing that fact and coming to grips with that only enhances your appreciation for life. So I think we should recognize that we die and nothing happens more. I don't think we should continue to sugarcoat things. Because I think that if we really understood, we would far more appreciate this life, knowing how finite and fragile it is. All right. I keep saying I want a show featuring you teaching adult science. I'm not a teacher, though. I'm not a teacher. I'm not a good teacher. I don't have the patience to be a teacher either. I think, though, we need more science in the media. I mean, how much science do we really hear in the media these days? We hear about rockets exploding. We hear about asteroids sometimes, but it's always the doom and gloom. It's always, or they're all going to die, or aliens. It's never real science. That's the problem. It's as if the standard of intellectualism has decreased so much. The bar is now so low that nobody cares about science in the public space. Nobody really cares about it much. We've taken it for granted. And we see corresponding decreases in science literacy in this country. A lot of people don't even know that the earth revolves around the sun. A lot of people are succumbing to conspiracies, flat earth. I think this speaks to many fundamental problems. One of them being the educational system, which I think is not adequate. I think that the media has done a terrible job in exacerbating this science illiteracy. We need more science educators. We need more science communicators. And I think we need more of that. That's what I try to, that's why I do this. I'm not here to teach you. I'm here to inspire people to be science literate, because anybody can do that. Every person can be science. I don't mean become a scientist. I'm not here to say you should be a scientist. No, what I'm saying is every person, especially today, should be literate to some degree in science. Not only is it good to know things, but it's good to know how to think critically. Know how when somebody tells you, well, what's your source on that? You know what a source is. When somebody tells you the earth is flat because you need a container for air, well, you know how to respond to that. Well, no, you don't need a physical solid container. You just need gravity. Gravity is the container for air and pressure on this earth. We need people who understand how to combat the misinformation. And I think every person, especially in a country that depends on science and technology, we should all be literate. And because science is more than just knowing things, it's a way of thinking about the world. It's so beneficial. It's so important. It empowers you to be a better person. Okay. How do you educate people about climate change? So I think what's happening is people are tired of being told, climate change is getting worse and oh no, we're all doomed. I think we're tired of the gloom. People are hungry for solutions. People want to know what to do. How can we solve this? And so we got to stop focusing on the doom and gloom. We should be focusing on the solutions. Solar, wind, energy, geothermal, renewable technologies, electric vehicles, plant-based, reduce the meat consumption, right? All these things, the way we do plastics. We need to focus on the solutions instead of saying, oh, climate change is a problem. We need people, because look, once the people understand the solutions, they're going to vote for the solutions. They're going to vote for the candidates who know the solutions themselves. That's what's happening. That's why we keep voting for Trump, because the people don't understand science. So they're voting in science illiterate leaders. And they're working against our best interests because, again, of their ignorance. So again, if we don't change, we're going to get stuck in this cycle of science illiteracy. Okay. Hey, Mike, the Big Bang is the expansion of the universe, so we truly don't know if it even started. Yeah, the Big Bang does not mean the start. This is a common misconception about the Big Bang. It does not mean that the universe necessarily started 14 billion years ago, because when we say the Big Bang happened, we say our local space-time expanded rapidly that time. It's a point in time where the universe is hotter, smaller, and denser. It's not the beginning of everything. There may be other Big Bangs beyond ours. There may be other universes beyond ours that are going through Big Bangs. So we don't know. If it doesn't speak to an ultimate beginning. It can speak to a beginning of our local space-time, but not the ultimate beginning of everything. This is a very important point that people should understand. Would you want to go out in the universe, like travel, study, and explore? Personally, no. I'm afraid of heights. I don't. I get squeamish going in planes. I would never want to go to space in a rocket. I love Earth. I think Earth is a fantastic planet, and the fact that we can study the universe from here, from the comfort of our home, is all I need. How is it possible to conceptualize when the universe didn't exist? Absolute nothing. Well, maybe there wasn't, and maybe nothing doesn't actually exist. Maybe when we say nothing, there's no coherency behind that. Maybe it's just logically incoherent to say nothing. Because even in empty space, right, you can say, well, nothing. Well, there's nothing in this closet. Well, there's air. Well, okay, take the air out. It's a vacuum. But that vacuum still has a vacuum energy. There's still energy in vacuum space, in the vacuum of space. It's quantum energy. There's still something there. Okay, well, take that out. But there's still space. There's still there's still a closet. There's still a boundary. You can't escape the fact that every time you think of it, you're thinking of something. Right? Every time you think of nothing, you're thinking of something. And so maybe it's just fundamentally incoherent to even talk about absolute nothing. You know, that's just my view. I think that there only is something. Please recommend a book. Anything Sean Carroll, Brian Greene, Neil deGrasse Tyson, you know, the pop scientists, even though, you know, they're still great, you know, even though they're not every scientist, they're not extremely rigorous in the books they have, they still have some great introductory science. Carl Sagan, one of my heroes. Anything he wrote is a great introduction, especially Cosmos, right? The documentary Cosmos is a fantastic introduction to science. I have the Demon Haunted World here. This book's about critical thought. It's about science literacy, the very things I'm talking about. It's about science, how it empowers you, how it changes your life, how we need to use it more. Every time you think of nothing, you think of something. Yeah, look, guys, even though I love delving into these philosophical things, it's just not worth your time to sit there and ponder about nothing, you know, like, what is nothing? Is nothing something? Is that... Some of these questions are just never going to be answered properly. And so having an existential crisis, thinking about these things, is not really worthwhile in my eyes. I think it's far better to just recognize that there are some things we'll never understand and keep learning as much as you can. That's it. You can get stuck in these philosophical jams where it's like you're trying to find an answer so bad and you don't have it, and you get stuck in these very deep questions. You don't have to go to those places and get... It's not worth your time. The human... there's only so much that the human body can take, right? Our nervous systems are only so fragile. You can't, pondering so much about these philosophical questions and these existential questions, thinking about them so much is so toxic. It's so bad for your nervous system. Okay. When seeing stars from here, how are they still dots traveling light years? I don't understand your question. Light years is a unit of distance, right? It's the distance that light travels in a year. That's a light year. But when we see a star from the night, when we look up in the night, they're far away. They're 4 light years away, but they are moving with us around the galactic center. And so, in actuality, their coordinates are not moving that much relative to us, right? So that's why they're still there every night. More importantly, the light from them takes, 4, 5, 10 years, depending how close or far away. It takes years to get to us. So when you look at the night sky, you're seeing the stars as they were years ago because it took light from them to reach us in years. So you're kind of, in a sense, looking back in time when you look at the night sky. Even the moon, when you look at the moon, it takes about a second for light to get to the moon and get back to you. So you're looking at the moon as it was a second ago, because it takes time, a finite speed, to get to you. What is the color of the sun? White. Look, this is important to understand too. Colors are not real. They're made up by the brain. Color is your experience through your brain. White is just how we perceive the sun, because the visible spectrum of light, which our eyes can perceive, the different wavelengths correspond to different colors. And so the sun creates all kinds of colors because it's creating all kinds of light all across the visible spectrum. So we perceive the sun as white, but as it goes through the atmosphere, the sunlight goes through the atmosphere, it can make it look yellowish. As the atmosphere kind of screens off certain wavelengths of light. And refraction occurs, and certain light beams don't reach your eye as it enters the atmosphere. But yes, it's technically white because it contains all the colors, but still, colors are not real. The universe doesn't see colors. The universe doesn't know colors. All right, Okay, if you placed a giant mirror 100 light years away, we could see Earth as it was today in 100 years. If you placed a giant mirror 100 light years away, we could see Earth as it was today in 100 years. 100 light years away. Well, it would take 100 years for the light to reach that mirror, and then 100 years to reach the Earth. So you wouldn't be doing anything. And the only way you can look back in time is if somehow you were to travel faster than light and observe the light before it got there. That's the only way you can see Earth back in time with light. you'd have to travel faster than light itself to escape light and then look back at it as it gets to you. That's not possible. So no, people say this all the time. Well, what if you can't travel faster than light for this to happen? Now, other planets out there might be looking, maybe let's say they're 70 million light years away. Let's say they're in another galaxy, right? A distant galaxy with a large enough telescope, they may be able to see the dinosaurs. If they were to look at the Earth, they would still see the light as it was reflected off the Earth 70 million years ago. But again, you need a very big telescope for this to happen. You need a gigantic one, bigger than the Earth, to see such a distant object that is so small. Why is our Earth a pale blue dot? How doesn't it change color then? It's the same as here. What? The Earth reflects blue light because of the oxygen, the water, right? Oxygen refracts blue light. In other words, sunlight comes in, all the colors, but oxygen molecules, they refract the blue. They absorb all the other colors. They absorb all the energy from the other light, but they refract the blue, the wavelength of the visible spectrum that is blue, that we see as blue. And so that's why the Earth appears blue from space. When using telescopes, do you see the past or current? You're always looking to the past. You're always looking as it was in the past when you look out into space, especially deep distances into space. If you're looking at a star 10 light years away, you're looking as it was 10 years ago because that's how long it took for light to get to your telescope. Light is not instantaneous as we think, right? We naturally think, oh, light's instantaneous. It's not. Light travels at a finite speed. If we look into the past, and if the object looks at us from the same range, is there a paradox here? If you look into the past, and the object looks at us from the same range, is there... Oh, no. So I see what you're saying. So if there was a planet, let's say a light year away, and we were looking at that planet at the same time as they were looking at us, remember, the light coming from them would have taken a year to get to us. So we're looking at them as they were a year ago. We couldn't see them in the current time. And this likewise for them. They are seeing us as we were a year ago from their perspective. So there's no paradox. Why is the ocean blue, but water does not have a color? Technically, it does have a color. Of course, if you put a handful of water, scoop a handful of water in your hand, it doesn't look blue. But given enough light, given enough size and distance, it's going to look blue. Because the way light refracts through the substance. So the sun is not a giant fireball. It's not fire. The sun is not fire necessarily. It's plasma. It's not a combustion process, right? Fire is the result of combustion, where you have wood or whatever, organics, carbon, being heated to a certain degree. But the sun is not doing that. It's not burning wood in its core. It's fusing atomic nuclei. And so the energies in the sun are so great that it's a very superheated gas. And you know, the atoms are very much more energetic. Why is the sky blue? Again, because oxygen likes to refract the blue. It absorbs all the other colors, but it refracts the blue. And that's why you see blue in the sky, because sunlight comes in and it gets refracted all around the sky. And if you notice, when you look straight up, it's darker blue because there's less sky. When you look up, there's less sky in your way, versus if you look at the horizon, especially on a beach or something, you're looking at the horizon, the sky looks whiter. It's a paler blue because a lot more air, there's a lot more air between you and the horizon. And so when the sunlight comes in, it's refracted a lot more. A lot more blue is being refracted. And that's why it looks paler from farther distances. That's exactly why when the sunset happens, when the sunset occurs, the sky looks redder, right? The sun is not yellow outside. No, the sun is still white. The sun is white anywhere. But yeah, they still see it. They would see it as white. Why is the Earth not flat? Because we can measure the rotation. We can measure if you look at the different shadows of objects at the same time of day at different latitudes. In other words, if you had a stick, let's say skyscraper, right? Skyscraper giving a certain shadow at the same time of day, but in London versus the same skyscraper or different skyscraper, same length in Egypt, all the different latitudes, the same time of day, but the shadows they would cast are two different lengths. How can that be? If the Earth is flat, we would expect the same shadow lengths, but they're different. That is proof that the Earth is curved, their surface is curved. And this happens across the entire planet, so we know the Earth is completely round. This is the basics of the basics. People discovered this thousands of years ago. If the sky blue but space is black. Yeah, well, space is black. It's not really color. It's just there's no light. There's just a lack of light. That's why it's black. But the sky is blue because we have light and atoms in the atmosphere. We have a lot of oxygen atoms, and it happens to be that blue is refracted off of the oxygen atoms. It's not completely round. Yes, it is. Yeah, technically it's not there. It's a little bit. It's like a pear shaped. It's a bit fatter at certain parts, but it's essentially completely round. It's not a flat, not remotely flat. That's the point. I mean, to even the fact that people are asking that question, it doesn't mean that they're stupid. I don't think that's the case. I don't think anybody's stupid. I think what's happening here is they were never taught how. They were never taught the how, right? We just assumed They went through the entire educational system never knowing how the earth is round. They were just told that it is, but they were never taught how. And we see this across all kinds of different conspiracies, right? People not understanding the how. They're only told things, but they're not told how. They're not shown how. You know. Speaking of which, is it the fattest at the equator because the fact that it's spinning? Its spin definitely has a lot to do with how the Earth formed, yes, but I'm not exactly sure how much. It has to do with gravity. It has to do with how the Earth formed, but I don't know how much either factor in. Does the sun go into the sea at night? No. The Earth rotates. That's why it seems like the Earth is that's why it seems like the Earth is setting, but it's not setting. The sun isn't moving that much relative to us. It's actually the case that we are rotating, and that's why the sun sets. How do we see a bunch of colors at sunsets? Why isn't it just blue? Because the sunlight is angled at such a different level during a sunset that it has to go through a lot more atmosphere to get to your eye. And that's why a lot of the blue is scattered away, is refracted away before it gets to your eye, leaving the red. In other words, the blue gets scattered. The red is what reaches your eye. Fact, I heard a dot on an eye is how large the sun is in the Milky Way. Oh, the sun is, compared to the Milky Way, the sun is a tiny, tiny speck. Science can't tell you everything. A lot of people are saying this now, right? A lot of people are saying, oh, science doesn't say everything. It can't tell you everything. But it tells us a lot. That's all that matters. We don't need to know everything. There's no one field of anything that tells you everything. Philosophy has its limits. The idea that science is supposed to tell us everything is ridiculous. It was never what people thought. If the sun is real, why don't we go there? Because it's hot. It's too hot to survive, even. Why is the Earth not upright? It's angled to one side. Yeah, it's on its axis. It's just the way well, number one, it could be because during the early solar system, there were lots of other planets that existed that no longer exist today. There were large bodies of large planetary bodies that were competing with each other for orbit. And the Earth likely was struck by not just one, but perhaps multiple planetary bodies that knocked it on its axis in that sense. Also, the way the Earth formed wasn't perfectly symmetrical, right? Very little small effects can have little small factors can have a big effect on how the Earth is angled. Can you explain how black holes are made? I find it interesting. Well, most black holes are stellar black holes. They have the masses of stars, and they form due to those supernovae, those stars that are so massive, about 20 times as massive as our sun, and they either explode, and when they die, they leave a corpse of a neutron star, essentially. And this neutron star is the neutron star is there in the core, but the supernova happens, and there's so much gravity that a lot of the material from the supernova comes back onto the neutron star, and it breaks the binding of the neutrons, and that neutron star collapses in on itself. It implodes, and it becomes a black hole, right? So that's how most black holes happen that way. Sometimes the supernova doesn't actually burst. Sometimes it just automatically implodes into a black hole from the neutron star. Now, our sun will turn into a white dwarf. The white dwarf is held by electrons. There's a kind of force that electrons generate that keep a white dwarf together, right? Because you might be asking, well, if the white dwarf isn't making starlight, why is it the case that it's held up? What's holding it up? Well, it's the electrons inside of the white dwarf that keep it together against gravity, held up against gravity. However, when you get enough mass, even that can break. Even the white dwarf can collapse. And that white dwarf turns into a neutron star and sufficiently large stars that are 5-10 times more massive. They turn into neutron stars. So a lot of stars turn out to be just neutron stars or pulsars. But again, if there's a sufficient mass, 20 or 25 times the mass of our sun, these stars turn directly into black holes when they die. It's fascinating. So yeah, a black hole is just a bunch of mass. That's all it is, right? And for more supermassive black holes, like at the center of our galaxy, that probably occurred because of those large early stars that were very clumped together in the origin of our galaxy, and they just collectively turned into black holes, and the black holes merged together and made larger and larger black holes, because that's what happens. When black holes merge together, they just create a larger black hole. And so that's likely what happened for the galactic center. At the center of our galaxy is a big supermassive black hole that we're all orbiting around. It's crazy to think about, but literally we are orbiting around a giant black hole. And it has the mass of a few million, about 10 or a couple dozen million stars. But maybe only a few million miles across. It's a massive black hole, but still, could it formed because of just lots of clumped up mass during our galactic formation? And all around our galaxy, could there be black holes lurking the size of that, with the mass of a star? That's also why we have lots of pulsars in the world, in the galaxy, because those are the corpses of dead stars. How do you know this? Can you see it? You're just repeating stuff. See, this is precisely one of the problems, right? We're never told the how, we're just told what. Because nobody really cares about, they want to hear the why, or that they want to hear the what. But how we know all this is through centuries of investigation and centuries of inquiry in science. We look at telescopes, we look at the size of stars, we look at the brightness of stars, the luminosity, and we can measure, oh, if they're this luminous, we can infer their sizes. Because we know how heat works on the Earth, and we know there are certain thermodynamic laws, and that would apply to stars. And so we know their luminosity, we know their brightness, we can infer how massive they are. And we take Newtonian mechanics, we know how the planets move around those stars. We take Einstein mechanics, physics, I mean, we understand how gravity would collapse those things and turn them into neutron stars. And we understand physics, like atoms, particle physics, right? We know how that works, and so we can infer based on particle physics what kinds of stars will be produced, right? What kinds of neutrons, what kinds of nuclei. It takes a lot of science. And so, yeah, we know how all this stuff happens, not because somebody told me, but because we can do the science. We can actually perform and demonstrate this scientifically. We're making lots and lots of inferences based on evidence, based on data that we've collected, have accumulated for centuries. That's how science works. Right? How do we know if I'm walking on the beach and I see footprints? You might say, well, somebody was walking there, but how do we know that? I didn't see that person walk. Well, we can make an inference. We know that when you step on the sand, it makes an imprint, an indentation on the sand. And we go, oh, okay, well, we can infer that there must have been somebody walking there. And then we can infer further. We can measure how large this imprint is. And go, oh, well, we know this person's shoe size or foot size based on how big the imprint is. Okay, well, then he must have been this large, because we know people with this foot size are typically this tall and this fat and this weight. And so we can also measure the distance between footsteps, and we can infer how long their stride was as they walked. We can infer the size, the shape, the weight of this person by looking at just the footprint. That's how science works. Even with just looking at a single footprint, when you investigate it further and you reflect back on background knowledge and already understood things, you can make really amazing insights with just looking at one thing. What makes mass have weight? Force. Gravity. We are being constantly held on by the Earth's gravity. That gives us weight, right? The fact that I'm pushing against the Earth's surface, we can assign that a weight. That's all we're doing. This dude is so lost. He believes in scientists and climate change. Climate change is a fact. We can observe it. We observe the climate warming up. We know it's warming up. From evolution, did humans come from just one sea animal, or was it from multiple? You mean sea animal? Well, Evolution, well, it wasn't, when you ask where, did we come from one animal? It's the case that our ancestors, there were many of our ancestors were aquatic, sure. But it's not to say that they were all alive at the same time, right? It wasn't like at the same time, there was many different animals that we come from. No. If you went back, if you traced back our evolution, you'd find species, single species that we emerged from. But there's many different species that preceded us. What are your thoughts on the Bible? It's a very interesting book. It has great poetry, great literature. It talks about some good morality, But other than that, it's, I think, a collection of stories made by people who didn't know much about science, and they accumulated these stories as a way of dictating and controlling people and establishing laws for their nation, for their country. That's all it really was. I think it was just a means of controlling and instilling laws. So there's nothing wrong with having laws, right? But the problem is that they're not true anymore. We don't take them seriously anymore. Don't eat shellfish. Don't work on Sundays. We don't really take that seriously. That doesn't apply to us at all. And that's why it was written at a very different time. So I don't think we should take the Bible seriously in that way, especially in where it makes these claims about reality that are just baseless. I have a degree in geoscience. Do you have a personal take when it comes to aliens or just ET life outside the galaxy? I suspect that there's lots of life out there in the universe because it formed so easily on Earth. People all the time think abiogenesis is so unlikely, but if you actually understood the Earth and Earth science, that life happened so fast. Almost immediately after the Earth had the right conditions, life emerged, And so it seems to me that life forms very easily in the universe. We know that lots of planets are made of water. In our own solar system, almost every planet has water on it. Whether inside of it or on it or in its atmosphere, there's water everywhere. Amino acids, very common. We also see those on space rocks all the time. We've seen amino acids in very complicated organics on Mars, on moons of Saturn, space rocks, asteroids, the moon. Amino acids is clear that the building blocks of life are common in the universe. And so I think there's plenty of life. It's just a question of what kind of life. Is it dumb? Is it smart? Is it bacterial? I think it's mostly bacterial life. I think it takes a lot. It takes a long time and very stable conditions to yield complex life. That's for sure. It took the Earth about 2 or 3 billion years to get complex life, like multicellular organisms. It took that 3 billion years. That's a long time to get to multicellular life. Let alone intelligent life. It took another billion years from that moment. And so we're talking 4 billion years to get to even a single intelligent species capable of generating radio waves and or communicating with radio waves. And so I think that intelligent life is far less common. I suspect that in our galaxy, even within 400 billion stars, there may be only 1 or 2 or 3 intelligent civilizations. So I think we're only one of a handful in our entire galaxy. I think it's that rare that such intelligence arises. I think it's that rare. However, given the fact that there are trillions of galaxies in the known universe, there's trillions of instances of intelligent civilizations, many of which have perhaps come and gone. Perhaps some of them, some intelligent civilizations rose. They got sufficient technology like nuclear bombs and ability to control for climate change, and they died from those things. Perhaps they self-destructed because of war, violence, or fighting. And so there's a kind of bottleneck where you only get a certain amount of intelligence thriving given all these factors. And even us, we're still just in our adolescence, in a sense, in our intelligence. And so we're just beginning to be civilized, and perhaps we might go extinct soon. I think whatever the answer is, whether we're extremely rare or extremely not rare, I think it's remarkable that we're here, and space is so vast that we could never, it's highly unlikely we'll ever be able to communicate with another such civilization. So I think we should take this as a lesson to embrace what we have, embrace our lives, embrace our civilization, and make it the best. I think that's the lesson from all this. So yeah, thanks for watching, guys. I think that's all. There's no way you can explain the evolution of humans in under a minute. It's just too complicated. I mean, I could, but you would lose a lot. See, when people want simplicity, people want things to be simple. And that comes with a cost. The penalty of wanting things to be simple is that you lose the complexity. You lose the nuances that are highly important for understanding the whole idea. And so people want things instantaneously now, right? Oh, just tell me the answer. But there's a value in taking time to learn all the different nuances. Otherwise you lose clarity. So even if I were to make a 60-second statement about human evolution, it wouldn't be very clear. Even if you understood every word, it wouldn't be clear, or as clear as it could be if I actually went and you understood all the science behind it. So that's the problem. Today, everybody wants things fast and simple, but that comes with a cost. That's why you have to be extra patient. Teachers and students need to be extra patient and understand why they're learning what they're learning. Otherwise, people get bored and that's it. They don't learn anything. That's what we're struggling with in schools today. And so, yeah. Are humans designed to eat meat? Well, if we were, why is it that we get disease when we consume even a normal amount of meat? It raises a risk of disease. I think that it's clear that our evolution entailed much more plant consumption than meat consumption. We look at our fossil records, our dental records in ancient sites, and we find that they were eating lots of plants. Hunting is extremely exhaustive. It's very energy intense. It takes a lot of work to hunt an animal and bring it back to the tribe, and so hunting, although was crucial for our evolution, it wasn't what we did mostly. I think we mostly were foragers. We mostly consumed fruits, vegetables from the ground, roots, things we can pick with our hands and cook in a fire. It just doesn't make sense that we would eat mostly meat. That doesn't make any sense. It makes sense that we eat mostly plants. And of course, some meat. But again, even in the past 10,000 years, most human cultures ate very little meat. Especially with the advent of agriculture, very few people were consuming meat on a daily basis, especially the way we do it today. Today, we consume the most meat today than we've ever done, because it's mass produced now. We have mass production of meat, and so that's why it's so much more accessible. Vegetables are not the hardest food our body can digest. They're actually vegetables are the best thing you can digest, because they have fiber. No evidence for that vegan claim. We're not talking about veganism. No, there's no anti-nutrients. That's more nonsense. There's no science that shows anti-nutrients are a problem. The doctor told me. Well, some doctors don't understand nutrition, right? Doctors only have so much they can, especially physicians, or there's only so much they understand about nutrition. There's all kinds of doctors who say we should be, eating all kinds of gross things and ridiculous things. I wouldn't take just somebody's word for it. I would look at the science, look at the evidence. So what does the evidence demonstrate? The evidence shows that you can be very healthy without consuming meat. So, if not healthier. So yeah, that's all, guys. I hope you enjoyed. Very grateful that I can be on TikTok and talk to you guys. Very grateful. What is the biggest misconception people have about science? The biggest misconception about science is that it's just this machine that spits out facts that we just have to believe. That's not what science is. Science does not mean you just go to a scientist and he just tells you things and you just have to believe it because that's fact. That's not what science means. Science is a meticulous, rigorous method in which you're investigating, you're questioning, you're poking at things, you're experimenting. And then you form conclusions based on the best evidence. And then that science gets tested amongst other peers. Right? That's how science works. It's not just, oh, what did the scientists say? Okay, well, I just got to believe it. That's not science. Too many people think science is just about asking what science, it's just about referring to a scientist and whatever he says is correct. No. It's a way of thinking. It's a way of thinking that affects every aspect of your life. Your finances, your health, your ethics. They're all influenced by your scientific way of thinking. Science reaches into more than just knowing about facts. It reaches into the way you live, the way you see the world, the way you interact with other people, the way you question things, the way you ask questions. It's one of the most important things one of the most important tools you can have, especially today where we are doused in misinformation and constantly confronted with opinions and beliefs and thoughts and sayings and statements and all that stuff. You can get very easily lost if you're not careful, if you're not scientifically literate.